So today we are looking at the singular value decomposition (SVD) of a matrix, and let's trace back. Let's see how we got here. Looking backwards, this is SVD. Just before this, we did the QR algorithm. To find the eigenvalues, eigenvectors. Before that was the power method. And both of these methods we got into because we wanted to look at non-linear problems. For example, finding the eigenvalue and the eigenvector is a non-linear problem. And before non-linear problems, the only thing that we would have done was linear problems. So in linear problems, we try to solve Ax equals to b. While solving Ax equals to b, we look at the linear least squares. When Ax equals to b is not properly solvable, when Ax equals to b is properly solvable, we do LU decomposition, something that I did not make a video of. Anyway, linear least squares, and in linear least squares we did the QR decomposition, which was inspired by the perpendicular projection thing. And before QR decomposition, this was also inspired by the normal equation. A transpose A X is A transpose B. This solves that linear least squares problem. That becomes the QR decomposition. That's it. What else before that? Before that, we saw the stability and conditioning of the problem. Stability of an algorithm and conditioning of the problem. So can I recall from memory the condition number of solving all of these? Let me think. So the condition number for solving linear is the kappa of the matrix A, which was norm of A times the norm of A inverse. This is what I remember. Non-linear problems, that is solving the eigenvalue problem. So solving the condition value for eigenvalue, the condition number for eigenvalue lambda is 1 over the cos of the angle between left eigenvector and right eigenvector for the same eigenvalue. And similarly for finding the eigenvector, it's 1 over lambda minus lambda, the minimum of this. Minimum of the modulus of this number, whatever that is. So that's the condition number for finding, the eigenvector. Power method, Q algorithm are just implementations of those. So now we come to the SVD. Finally, let's get to the SVD. Okay. Singular value decomposition. SVD. So let A a general matrix of m cross n. A singular value decomposition of A is a factorization of this form. A is U sigma V Hermitian, where U is an m cross m, that is for the first order of dimension, is a unitary matrix. A unitary matrix means U Hermitian is identity, and U Hermitian U is identity. I think that's what unitary means. However, let me just verify. Yep. So unitary matrix is U star and U is, and U star is identity, and they're inverses of each other. So that's unitary matrix. V is a unitary matrix from the right hand side with a dimension n cross n, and then the sigma is a diagonal matrix, which is an n cross n matrix. Now the diagonal entries sigma j of sigma are non-negative, so they are always greater than or equal to 0, and in non-decreasing order. Non-decreasing. It should be non-increasing. That should say non-increasing. Yeah, it should say non-increasing. So that the sigma 1 is greater than equal to sigma 2 is greater than equal to, and so forth, where P is the minimum of m cross n, minimum of m and n. So the diagonal matrix is real and has the same shape as A even when A is not square. The matrices U and V are always square. Alright, that's just the singular values. These are just the singular values of the matrix. Now what is this? Let me show it in pictures. So the image of a unit sphere under a map A is a hyperellipse in Rm. Thus with A, U, sigma, V Hermitian, we have the unit, okay. So let's say my A is an M cross N matrix, right? If my A is an M cross N matrix, that means when I apply A to some vector X, that vector is of the dimension Rn. And it goes to the dimension of Rm. That's what this linear map A does, right? If it's a complex matrix of M cross N, it applies to a vector in the dimension Rn, and it goes to a vector in dimension Rm. So what happens is, let me write A as U sigma V Hermitian. So U sigma V transpose or Hermitian times X is equals to AX, right? So the first thing that happens is I apply a V to X, and that V is just a unitary map which preserves the shape. Rotating a sphere is a sphere. So all this V does is just rotates and moves my axis of that sphere. Instead of just facing towards the x-axis, y-axis, z-axis, now my sphere is rotated and tilted, and just overall apply some angle to that sphere. So now the sphere is still a sphere. Now the diagonal matrix sigma, what it does is stretches the sphere into a hyperellipse aligned with the canonical basis. So this sigma, like I said, can be of this form. A diagonal, and then a diagonal only goes to here and then zeros, or it can be of this form. A diagonal up to here and then zeros all around it. So it can squish some directions or create some new directions with zero component, etc. And then the U, the final matrix U is again a unitary map that rotates or reflects the hyperellipse without changing shape. Okay. This is just U sigma V transpose.
Building's closed, it closes at 5 on Saturdays.
5?
Yep. Finish up when you finish.
Yeah.
When you finish.
Okay,
Talk
so
to somebody,
how much time do I have?
5 o'clock.
Yeah, so yeah.
Whatever you're doing,
Yeah,
just finish.
yeah.
Whenever you finish, then you leave.
Okay,
Your
yeah.
discretion.
Yeah.